Our video today will discuss a fourth application for linear systems of differential equations to combat models. As an example of a problem, let's suppose that we have two armies, which we'll hypothetically call the Starks and the Lannisters, engaged in an open battle. Each Stark can kill an average of A Lannisters per hour, while each Lannister can kill B Starks. If the initial size of the Lannister army is twice as big as the initial size of the Starks, how much bigger does A have to be for the Starks to win? In other words, if we have an initial deficit in the number of Starks compared to the Lannisters, how much more efficient will the Starks have to be to overcome this difference? To begin, we need to set up a system of two differential equations for our two dynamically evolving quantities in this problem. One of those quantities, S of t, will be the size of the Stark army. The second, L of t, will be the size of the Lannister army. Applying a similar reasoning to that used in deriving our fish population model during class, we can see that the rate of change of S should be proportional to the size of L with a negative coefficient. To understand this, note that each Lannister will kill B Starks per hour, so if there's L Lannisters, then the total number of Stark deaths will be B times L. Of course, we're assuming that there's no reinforcements which will arrive over the course of this battle. Second, a similar line of reasoning will imply that L prime is also proportional, but this time to S. The more Stark soldiers there are, the more Lannister deaths there's going to be. If we define a solution vector, in this case, as tracking the Stark and the Lannister armies, then we can rewrite this system of equations in matrix vector form, where our matrix A now, the coefficient matrix, would be 0, negative B, negative A, and 0. Let's see how all this gets plugged into Matlab. Opening up a live script, we're going to assume that the Starks initially have 15,000 soldiers, or that S of 0 equals 15, and that the Lannisters initially have 30,000 soldiers, or that L of 0 equals 30. Although any initial conditions where L of 0 is 2 times S of 0 will lead to similar results. As a first attempt at figuring out what the Stark's kill rate needs to be to overcome this deficit, we're going to set their kill rate equal to twice the kill rate for the Lannisters, or A equals 2B. We're going to just set B equal to 1, which would make A equal 2 in this case, although again, you can play around with other values of A and B with the same ratio and see that the results will be similar, although the time scale may be different. The first step in solving systems of equations with Matlab is to define your coefficient matrix A and your initial conditions y0. Once you've done so, since this is a linear homogeneous system, we can simply define our rate function as A times y. I can enter my initial conditions as y0, and I can enter my t interval as 0 to whichever time I want to run the battle up to. We're just going to try 1 hour here to see what happens. When we run this code, we're going to see something interesting happen. We're going to see that, one, the Starks do seem to lose this battle. They hit 0, it looks like about 3/5 of the way through the hour. But they don't stop at 0, they start going into negative numbers after that. And as they go into negative numbers, the Lannisters start to gain in army size as well. You could think of this as a situation where the Starks get turned into White Walkers and those White Walkers somehow join the Lannister army. But we don't want that in our situation. We're just dealing with humans here. So what we really want to do is cut off these equations, these lines at the point where one of them hits 0. Because after that point, our differential equations which govern the dynamics are really no longer valid. The battle's over. You can include that condition by adding 2 extra lines to our code. And if we rerun our script under this new scenario, we'll now see that the battle ends when the Starks hit 0 in this case, and the Lannisters win with a hefty army size of over 20,000 people. So, twice the kill rate wasn't enough. What about 3 times the kill rate? Unfortunately, running the battle again under this scenario means that the Starks do kill a few more Lannisters and last now about 3/4 of an hour, but eventually it leads to their destruction. Take 4, although I can't count because this is actually take 3. Let's try A equals 4B. If A equals 4B, we see something a little bit more hopeful start to happen for the Starks. Notice that both army sizes go down fairly rapidly, but the battle lasts a little bit longer than before, and it looks like going out into 4 hours, no one has hit 0 yet, although there's fractions of the thousands of soldiers left, and they're kind of battling out for survival. So A equals 4b is some sort of equilibrium situation between the two where neither side really wins. Reaching an equilibrium type situation is good because that means if I bump this factor up a little bit above 4, that should be enough to get the Starks victory. And sure enough, trying 4.001, for example, means that after roughly 2.5 hours, the Starks have finally emerged victorious, the Lannisters are dead, and although they only have, less than 1,000 left, at least they won the day. I want to conclude this video by noting our investigations in Matlab actually demonstrate a classic mathematical result called Lanchester's square law. What Lanchester's square law says is just what we found, that in order for the smaller army to achieve victory, the ratio of their kill rate to their enemy's kill rate, A over B, has to be greater than the square of the ratio of their enemy's initial size to theirs. So if their initial enemy has twice the amount of troops, then they would have to kill 4 times as many per hour in order to achieve victory. These types of models have been used in modeling Civil War battles, in World War II battles, just to name a few. Of course, the assumptions that you don't receive reinforcements and that the kill rates are sort of linear in the number of troops are not very realistic in the sense of as the army sizes grow smaller, so do the number of troops that die per minute. If we have time later in the course, we'll talk about some nonlinear models which take into account these effects. But for now, if you can use this type of investigation in Matlab to look at solutions to systems of linear first-order equations, then I think you pretty much got the point of this video down.